Thank you.
Yeah, thanks, Alessandro. I don't want this to be a very technical talk, since most of you probably didn't really think about random field Ising model that much. So I want to explain the basic idea of what we did. So random field Ising model, let me define the model. So we take the usual Ising model on the lattice. It's a statistical physics model. And then you do something, you add on each lattice side, you add a magnetic field, Hx. And this magnetic field is a random variable. So it's a mean zero random variable. And okay, it has some root mean squared, which is not zero. And so the physical meaning of this magnetic field is that you have a model with magnetic impurities. So imagine you have some material, and through this magnetic material you have some special atoms which are randomly distributed through the lattice. And each of these, so there are kind of the lattices, the atoms of the material which represent the spin Sx, and then there are some frozen in atoms with their own magnetic moments, whose magnetic moments are frozen. So they take random values plus or minus 1, and they're not in thermal equilibrium. So the positions of these atoms are random. The values of the magnetic moments are also random. I'm just giving a physical picture. So this, you can keep this in mind as a possible physical realization of the random field Ising model. Not necessarily. You can think that the original material had the random field, this magnetic impurities, just distributed with some concentration throughout the lattice. In the material, but now I'm going to consider a model where a random field is present on every lattice. Okay. Yeah, not that. And so in such a situation, what is going to happen? So what is going to be the phase diagram of this model? And as a function of the temperature and of the strength of this random magnetic field. So the phase diagram is, up to some caveats that I will describe, is like this. So if there is no random magnetic field, then we just have a critical temperature Tc, and so we have a disordered phase on this side, and then we have an ordered phase on this side. So, I'll mention later what is the range of dimensions. But and then, so what is going to happen now? If we have an ordered phase, so if we have an ordered phase, so plus everywhere. And then we add a small random magnetic field, which can be positive or negative on every side. Then you can think naively that if this random field is weak, then it's not going to modify the ordered phase. So the model is still going to stay in the ordered phase. But then, of course, if you turn on a huge magnetic field, a huge random magnetic field, then the spin on every side is just going to follow the magnetic field applied on this side. So this means that, and since the magnetic field is random, on some sides it's going to point up, on other sides it's going to point down. It means that for very large random magnetic field, you are going to be in the disordered phase. While for small magnetic field, you feel that you are going to be staying still in the ordered phase. And so then you expect this sort of phase diagram. And so this expectation turns out to be correct as long as the dimension D is larger than 2. Because it turns out that in small dimensions, this naive expectation that small magnetic field, small random magnetic field doesn't destroy the ordered phase, it turns out to be incorrect, because you can always find, even though the magnetic field is very small, since it's random, you can find a big region where the average value of the magnetic field is positive, and then you can flip all the spins in this region, and then by doing such flips, you can show that you can disorder your system. So this is called Im-Riemann argument, and so this shows that in D smaller than 2, this picture is not correct. But today I'm going to talk only about D larger than 2, so where this phase diagram is correct. And it is believed that anywhere, if you approach this line from any direction, then you experience a second order phase transition. So there is an order parameter. Order parameter is a magnetization, average magnetization. And this, it is believed that this magnetization goes to 0 as you approach this line, that the phase transition is continuous. Now, this phase transition is in a different universality class compared to the non-disordered Ising model, which sits at this point. And so how do you understand this? From the field theory point of view, you can see that the Ising model fixed point is unstable with respect to this random perturbation. I'm going to write some simple equations which show that in a second. And so the simplest situation that you can imagine is that if you turn on this random magnetic field, this fixed point, pure Ising fixed point becomes unstable, and then you kind of flow against this phase boundary, and you flow to a new fixed point, which is located at the 0 temperature. And so this new fixed point is called sometimes random field fixed point. It has different critical exponents from the Ising model fixed point.
So the whole line is the second one. The whole line is
this whole line is the line of second order phase transitions, the universality class of this random field fixed point, because the whole line flows to this fixed point. Yeah. This is anyway what is believed to be true, and I'm not going to challenge this belief. I think it's pretty solid. So so this is this kind of basic things. Now let us go to the field theory of this model. And well, the field theory is obtained by taking the usual Ising model field theory with the quartic potential, and then we add a term to this Lagrangian, which is phi j, and j is the continuum version of this magnetic field. So j is some random field. So average value of j is equal to 0, and the 2-point function jx, j of x prime, is h some h times delta of x minus x prime. And well, what I would like to say in the rest of this talk is some theory which relates to the nature of this second order phase transition. And so that's why I'm going to use this field theoretic description, which is supposed to be good near this theory, near this phase transition. And to study this phase transition in a model with disordered couplings, you have to use some method, and the method I'm going to use to start the whole discussion is the replica method. So let me remind you some basic things about the replica method. So we take the model with this action S, and we write a model. We multiply the fields. So instead of having one field phi, we take model with fields phi1, phi n. So we consider the model with the action Sn, which is equal to the integral of d phi I squared plus v of phi I, sum I from 1 to n. And then you couple all of these fields to the same random magnetic field, phi 1, phi n. And in the replica method, we will have to take the limit n going to 0. But before we take this method, before we take this limit, we would like to get rid of this random magnetic field J. And the way we do it, we perform a path integral over this magnetic field with the measure, with the Gaussian measure, minus J squared over H over 2H. So we are basically assuming here that this magnetic field is distributed according to a Gaussian law, which reproduces our assumptions about the 1-point function, the 2-point function. So this is the simplest assumption. And so once you do this manipulation, you obtain an action of the following form. Let me also call it Sn. So it's sum d phi I plus v of phi I minus h phi 1 plus phi n squared. So, okay, so this is going to be our starting point for what is going to follow, but are there any questions about the methodology, why I'm using the replica method? You know, these are some a little bit, yeah.
Why do you keep only one magnetic field and not one plate replica? Essentially, this would mean you will have one more operate.
Well, what is the reason why I'm using the replica method? Is that I'm studying the theory with the quenched disorder. So this means that the correlation functions that I'm going to compute. So I would like to compute correlation functions of a bunch of phi's maybe, and then I would like to average them over the disorder. So this means that I have to take first, compute these correlation functions of phi in a theory with J, with certain J turned on, and then I have to average over J. So this is what I have. This is the kind of computation that I have to perform. And so the replica method, this guarantees that if everything depends analytically in n, that when you perform the computations with this action where all n copies of phi are coupled to the same J field, then this is going to reproduce for me this result. So the reason why I'm taking this n going to 0 limit is that inside this phi j, the way it's defined is that it's the integral of phi over phi e to the minus s of phi and j, a single phi and j, and then there is a partition function 1 over z, which also depends on j, And then I have to average over all j's. So this n goes to 0 limit. It's a trick to get rid of this partition function which depends on j. That you are fine with.
Basically, you start with one copy, which is 5 plus j.
Yeah. No. That because that's the replicas. All replicas, they are coupled to the same to the same field. So if each replica coupled to its own magnetic field, then you would completely factorize your problem into n copies. You would be doing nothing. You would be achieving nothing. Any other questions? N going to 0. Well, you can think about it also this way. So this n going to 0 means there's going to be like one copy, which is the physical copy, and minus one copy, which is going to kill this 1 over z in the denominator. But this 0, you can write it as 1 minus 1 or 2 minus 2, 3 minus 3. In fact, strictly speaking, in this limit n going to 0, you have access to infinitely many copies. We have no choice but to assume that it's analytic, as you will see. It's kind of. Is it? We hope it is. Yeah.
Usually, when the exam is well, zero limit, you get non-unitary.
Yeah. You don't necessarily see it yet, that the CFT is non-unitary, but in a few steps we will indeed see that our CFT is non-unitary, even though perhaps we are a little bit lucky and it's not logarithmic. It's non-unitary but not logarithmic. But already now you can see several things, like leaving aside this n going to 0 limit, which is a bit mysterious. You can already see that this perturbation that we are adding to our action is a strongly relevant perturbation. So it's a phi squared perturbation, and so this explains why the pure Ising fixed point is unstable. So we really know that by adding this perturbation, we are doing something really violent to our theory, and we can expect to flow to a new universality class. And so the question is, how are we going to learn anything about this new universality class, given that this perturbation is strongly relevant? Because typically we know that we can analyze flows if the perturbation is weakly relevant. So let me give you an example. Suppose that we had here, instead of phi 1 plus phi n, suppose that we had here phi 1 squared plus phi n squared. That would correspond to a different type of disorder in the Ising model. Instead of considering field disorder, we could consider bond disorder. And in that case, the problem would be easier to treat, because we've just had here some quartic interaction, some new interaction that you would have to add to your model. You could just do the usual epsilon expansion around 4D. Everything would be nice and easy. And in fact, bond disorder is a much better understood type of disorder in the Ising model. So here we have a difficulty. So we have this strongly relevant term. It's quadratic. But anyway, let us try to proceed anyway. So since the term is quadratic, the first thing that you can try to do is to compute the propagator of the field phi in the presence of this term. So, we just take this. So here inside the potential V, there is m squared phi squared term. And then there is this. So we just put this all quadratic terms together, and we compute the propagator. So it's an instructive computation, and the result of this computation is the following. Yeah. Well, in 2D, the Ising model is still unstable with respect to this perturbation. It just doesn't flow to a new fixed point, I think. Yeah. So you compute this propagator in momentum space, and you find the following answer. So there is, and you can do this computation for general n. And from the second term, you get a correction which has this weird form, p squared plus m squared divided by p squared plus m squared minus nh. So you compute this propagator and you see two weird things. So the first weird thing is that you see, okay, first of all, the first weird thing is that here you have p squared and here you have p to the fourth. That's something that we are going to talk about. The second weird thing you see is that here you have m squared, a single pole. Suppose that you tune mass to 0 to put the theory at the critical point. Okay, here you also have p squared, but here you have a different pole at the value of m squared minus nh. And you see that this second pole is not at 0 unless n is exactly equal to 0. So this has a very important consequence, that in this theory, the CFT is going to exist, if at all, only at n equal to 0. So that's weird, and that's very different from this bond disorder case. 1 squared plus phi n squared. I could do perturbation theory for any n. I would find the CFT, and then I could do an analytic continuation within this family of CFTs. I could take the limit n going to 0, and I would find the CFT which describes bond disorder. But here, I cannot do this. So the CFT is only going to exist at n going to 0. So what's going to happen in this theory is that as you increase n, as you take the limit n going to 0, so you have some range of distances x, and you're going to have a certain range of distances where your correlation functions are going to be scale invariant, and this correlation length. And this correlation length is going to go to infinity as n goes to 0. And only in the limit when n is exactly 0, you are going to have a full scale invariance at all distances. So that's also kind of weird. So it means that we do have to take a limit n going to 0, but for example, we cannot first compute critical exponents at non-zero n and analytically continue critical exponents. We really have to compute critical exponents at n equal to 0.
Should you have delta ij in this example?
Yeah, no, there is no delta ij. So here you have some, let me write here some matrix mij. And so this matrix mij has the property that it has all elements equal to 1 for any I and j. Okay, so this is a little bit weird, and let me now focus.
Slava?
Yeah.
So the perturbation is still relevant, right? So you're claiming that for generic n, it goes to trivial fixed point?
For generic n, it goes somewhere where I don't know where it is going to become gap theory. Yeah. So So let me now focus to this on this case m squared equal to 0 and n equal to 0, and then my propagator phi ij is delta ij over p squared plus 1 over p to the fourth. So you see two different powers of p in this propagator. So what does this mean? Yeah. At non-zero n, perhaps it will decouple, but it will, it will decouple later and later, and we are interested in the range of distances where that mode is also coupled, because that's the interesting range. What you are saying is that, okay, there is this range, which is the interesting range. And then, maybe here there is another range where you have some other CFT. And that CFT, as you take the limit n going to 0, it's pushed to longer and longer distances. Perhaps, yeah, I don't know. I never studied this CFT carefully because it was clear to me that it's not the interesting one. It keeps being pushed to further and further distances. Yeah.
And n equal to 0 doesn't propagate anything. So is it dimensions of analytic continuation or some kind of...
No, what do you mean it doesn't propagate anything?
There is no degrees of freedom at n equal to 0.
Well, as you will see, it's not that there is no degrees of freedom. You will see that there is, the way we will write this theory is that there are going to be some fermions and some bosons, and the partition function is going to be equal to 1. So the fact that n goes to 0 means that the partition function is equal to 1, because the partition function of the replicated theory is equal to the partition function of the non-replicated theory to the power n. In n going to 0, it goes to 1. But we know that the partition function can be equal to 1 because there is some constellation between fermionic and bosonic determinants. So there are degrees of freedom, but they conspire to arrange. Well, we are in Euclidean. So, but I want to say I want to focus attention on a different weird thing of this propagator, is that since their powers are different, it means that the multiplet of fields phi I contains fields of different scaling dimension. We cannot say that phi I has some dimension 1 or dimension 2. It's just some mix. There are some inside phi I, there are some fields which have dimension 1, and there are some fields which have dimension 2. So that's weird. That's also weird. And this fact...
But you broke the second term also breaks Lorentz.
It doesn't... Lorentz? No, Lorentz doesn't break.
Sorry?
It doesn't break Lorentz invariance. It's 1 over p squared. This ij is in the global symmetry. Yeah. No, but first of all, this tensor is in the global symmetry space. So you can say whether this term breaks SN invariance. It doesn't break SN invariance because this matrix Mij, which has all elements equal to 1, is a SN invariant matrix. You permute, everything is a SN invariant. So SN invariance is very important. And so, the fact that this fields phi I and this multiplet mixes fields with different dimension, it can play on you very, it can play on you jokes. For example, you cannot just look at the operator phi I to the fourth. Well, that's an operator that we would like to study, because recall that inside the V, inside the potential, there is phi I to the fourth. well, to be more precise, sum of phi I to the fourth, I from 1 to n. So this is an operator which is going to take our Gaussian theory described by the quadratic Lagrangian, and it's going to drive it to a new fixed point. We would like to know the dimension of this operator. That's kind of the first computation you would like to perform. But you cannot compute the dimension of this operator just by saying, okay, phi has dimension 1, so phi to the fourth has dimension 4. Because we know that inside phi there is a mix of two things. So what is the dimension of this operator phi to the fourth? Is it 4, or maybe it's 8? Well, I would like to argue that it has dimension 6. It's the middle ground. So how? Okay, so this is the first thing. So what is the dimension of this operator? In the limit n goes to 0, it has dimension 6. So how do you determine the dimension of this operator? How do you determine the dimension of operator in the conformal field theory?
Any dimensional space-time.
Sorry?
Dimensional space-time is
Well, we will see that the dimension of this OD is equal to, well, delta is equal to 2D minus 6 in D dimensions. Yeah.
Isn't this a contradiction to your assumption of an LP scheme? Because naively,
It's not a contradiction, but I'm just trying to.
I can compute, the nine dimension, this is
I claim that in this range, there is a certain range of distances where everything is going to depend smoothly on n, and this range is going to become larger and larger than in the limit n goes to 0. This is the picture.
around the UV fixed point, which is free,
Yeah.
any dimension, you compute the dimension of that object is definitely
Around the UV fixed point.
the free fixed point.
What you will see is that
Okay, go ahead.
it's a, you know, I mean I disagree with what you're saying, but I can explain later. Yeah. The limit n goes to 0 is smooth if done properly. So how do you compute the dimension of operator O in the conformal field theory? Well, it's very easy. You just compute the two-point function. So you compute the two-point function O delta, and we know that it has to go as C over x to the 2 delta, right? Well, unfortunately, this method is not going to work in our case because we are taking n going to 0 limit, and in the n going to 0 limit, this operator O is a singlet of Sn, so we sum over all i's. So in the n goes to 0 limit, any singlet has a 0 two-point function. So this coefficient C is going to be 0 for us. And since the two-point function vanishes, we cannot use this argument to extract the scaling dimension of O delta. Yeah?
Is it clear that this is a well-defined problem? I mean, couldn't this be mixing with something else?
Well, yeah. So this O delta is going to be let me call this O, right? So O delta is going to be a sum of several operators, like it's going to be O delta plus O delta plus 1 plus ... But I'm interested in the smallest delta which occurs in this sum. It's a well-defined problem. I'm giving you a pedestrian way to do this calculation, then I'm going to give you a much more powerful way to do the same calculation which gives the same answer. But better to do things this way first. So anyway, this way doesn't work, but there's another way which is a small modification, which also most of you will agree that it's almost as good. I'm going to compute the OPE of O delta with itself. So I'm going to compute the three-point function. So the OPE of O delta with itself in the conformal field theory is going to contain, there's going to be some OPE coefficient divided by x to the delta. If the operator O delta occurs in its own OPE, then by looking at the power of the prefactor, I can determine the dimension of O delta unambiguously.
Is the issue, sorry, well, first, this O delta is not the O54 that you write, or it is?
So I'm going, yeah, so O is going to be the sum of phi to the fourth.
Yes, but is it clear, so, okay, first, it's not clear that this is an operator that has about a fine scaling.
Yeah, I'm interested in the leading one, in the leading dimension contained inside O delta.
Right, but does that mean that there is just a change of basis that you should be doing, and then you...
Eventually, you will see that there's going to be some smart change of basis. Yeah. Yeah. But since that change of basis is a little bit too smart, I want to show you that it's really needed. I want to show you any calculation can be done without a change of basis. So I'm going to show you that you don't have to perform this change of basis if you want to work really hard. But if you want to work less, then you better perform the change of basis.
Can you say again why there is no identity?
Sorry?
Why there is no identity? You said,
Here in the OPE?
yeah, I didn't get the argument.
Well, the argument is this. So you take, so here there's some phi I to the fourth, some phi I to the fourth, phi j to the fourth, right? So let us perform this two-point function. Let's compute this two-point function by weak contractions. You compute some weak contractions. Whatever you do, in the end, you will have to do a sum over n identical terms, and you take the limit n goes to 0. So whatever you do, there's always going to be a factor of n in front, and you take n going to 0 limit, and it's 0. It vanishes. That's the usual feature of any singlet correlation function. So in fact, not just the two-point function, any n-point function of any singlet operator is going to vanish.
You still say I rescale the operator to get rid of it.
No, that would be wrong to do. We are not. We don't want to do. So the limit n goes to 0 has to be smooth. I'm not taking.
Well, it depends if you want to have the two-point function smooth or the operator.
Anyway, you can try to do this, but that's not the right thing to do. So let me then, because you see, it's natural that the endpoint function of O vanish, because we know that the partition function of this theory is 1, and it has to stay equal to 1 after the perturbation. So when you perturb the theory by a certain operator O, then the corrections to the partition function are just integrals of endpoint functions of O. So all of these things have to vanish. So this theory has some RG flow, but the flow is not felt at the level of the partition function. Anyway, let me do this calculation for you. It's very easy. So you take phi I to the fourth, times phi j to the fourth. You want to compute this OPE, and you want to find in the right-hand side something which is also proportional to phi to the fourth. Well, as you know, you perform this sort of OPE in free theory by doing weak contractions, and we have to do 2 weak contractions. So it's going to be equal to some constant times phi I, phi j squared. We're extracting 2 weak contractions, and then we have phi I squared, phi j squared. If you've done ever such calculations, you know what I'm talking about. And so we have this square of the two-point function phi I, phi j, and let me do it in the position space. Here it's in the momentum space. So I write in position space delta ij divided by x to the power d minus 2 plus, well, it was 1, but it has to be h, plus h divided by x to the power d minus 4 squared. Sorry, let me continue this direction. So if you take the square of this, there's going to be the term that you would like to pay attention to is the term proportional to delta ij, because once you contract delta ij with phi I squared, phi j squared, you get phi I to the fourth, which is what we started with. So you pick delta ij divided by x to the 2d minus 4 plus h delta ij divided by x to the 2d minus 6 plus the third term, which we don't need. And so this x to the 2d minus 6 tells me that the leading operator inside O delta has dimension 2d minus 6. And the fact that there is also 2d minus 4 tells me that there is an admixture. There is a second, there is also an operator here which has dimension 2d minus 4. But it's more irrelevant. So the most relevant operator has dimension 2d minus 6.
So basically always not a scaling eigenoperator.
It's not a scale, yeah, again we're discovering that it's always not a scaling eigenoperator.
Sorry, the term would be like x to the power 2d minus 8. You're saying this one.
It gives a different operator because it gives, since it doesn't have delta ij, it's going to give to me an operator of the form sum phi I squared squared. It's a different operator.
Is this how you're supposed to get the supersymmetry with the integer spacing, or is it
Not yet, not really yet. But I'll come to the supersymmetry in a second. So what, this I already gave for you some rigorous justification of the fact that in this model, the upper critical dimension is equal to 6. Because this delta, 2d minus 6, becomes marginal in d equal to 6. So if you've studied textbooks on this model, then you've seen that there are some usually a little bit voodoo arguments which are given for this d equals 6 upper critical dimension. But here we see that there's no need for voodoo. We just have to honestly compute the dimension of this O, and it's 2d minus 6. There's nothing to argue about.
Since the counting is a bit weird, it might not be entirely obvious that that any other operator is also not going to be right. But I guess it's easy to see.
Well, it's not exactly obvious, but okay, it's very suggestive. It's the quartic coupling. Yeah. So what do we do? Where do we proceed from there? We see that in this theory, something weird happens with these operators. We keep working with operators which are not eigenoperators of scaling dimension. So this is, of course, for a field theorist, is a pain in the ass. We want to find, we want to get out of this mess. We want to find the basis of operators which are good scaling operators. We want to work with this basis. So this is a well-defined problem. And this problem was solved by Cardi in '85. But somehow nobody appreciated this before our work. So here, there are some ways to justify this, to motivate this transformation, but I've already motivated this a lot, so let me just state it. He said, let me consider a linear transformation from phi I to a multiplet of fields which he called phi, curly phi, omega, and chi I. And these chi i's, they have indices ranging from 2 to n. And they satisfy a constraint that sum of chi i's is equal to 0. So the number of fields doesn't change. And this transformation is as follows. So phi 1 is equal to phi plus omega over 2. And then all the other phi i's are equal to phi minus omega over 2 plus chi I. So this is for I equal to 2n. And so this transformation is tailor-made. It has the following property that if you take the quadratic part of the Lagrangian from which we extracted that propagator, so minus IH phi 1 plus phi n squared, and you transform it to the Cardi variables, then you get something amazingly nice and simple, which is of this form: d phi d omega minus h over 2 omega squared, here it has to be h over 2, plus 1/2 d chi I squared, plus something which is of order n. Let me just give you an example. So suppose that I want to transform this I want to transform phi 1 plus phi n to these Cardi variables. Well, then I take phi plus omega over 2. This is phi 1. And plus I take sum over from 2 to n, phi minus omega over 2 plus chi I. And I see what happens. Well, chi i's, they satisfy a constraint that their sum is equal to 0, so this disappears. You have phi's, you have one phi here, and you have also phi's here, so everything gives you n times phi, and that also goes to 0, in the n goes to 0 limit. And then finally we have omega. And omega enters with different sign here and there, so you get plus omega over 2 plus n minus 1 times minus omega over 2. N goes to 0, and so you get omega. And so this omega is what we have here, minus omega squared. And the reason why this is nice is that now we can look at this new action and we can read off scaling dimensions of fields, and each of the three fields, phi, omega, and chi, has a well-defined scaling dimension. So omega has dimension d over 2, chi has dimension d minus 2 over 2, and phi has dimension d minus 4 over 2.
How do you work with this constraint, the sum of chi?
It's not difficult. So the propagator chi I, you don't have to work with this constraint. If you don't like it, you can solve it. But just the propagator chi j is 1 over p squared times matrix Pij, and this matrix Pij has to satisfy the constraint that the sum Pij over y to n has to be equal to 0. So Pij is equal to delta ij minus some constant times this matrix Mij.
But then in the perturbation, it will be not that easy to express.
Well, it looks complicated now, but you see, it's not going to be complicated in a second, because in this chi, how many fields chi do we have anyway? We have fields phi omega, 2 fields, and so the total number of fields is 0, so you have effectively minus 2 fields of chi, and as the next step I'm going to replace chi's by 2 fermions, and so that's going to be the end of our difficulties. Yeah.
So it looked before that H was dimensional, and now it looks like it's dimensionless.
Well, it's dimensionless because now I'm measuring distances in the scale of h. So h is the parameter which sets the scale of the problem.
I'm just wondering how you got the d over 2.
Of course, I'm treating h as a constant. I don't rescale it. Yeah.
And there? That's the difference?
Well, here it's the same H.
But their H has a graph.
Anyway, I don't, you see, these arguments that you are bringing up, these are some bookkeeping arguments which sometimes help you to see certain things without making calculations. But the definition of the dimension of a field in the Gaussian theory, it doesn't, you know, I have some parameter in my Lagrangian H. I don't have to remember whether it has mass or where it came from or so on. So the dimension of the field is determined by the scaling of its propagator. So you compute the propagator of omega. The propagator of omega is 1, well, so do you want me to write down the propagators? You could absorb it into omega, yeah. You could rescale omega to observe, but it's not what I want to do. So the propagators are phi equals h over k to the fourth. Phi omega is equal 1 over k squared. And chi is, okay, I already wrote it there. So these are the propagators. The scaling dimension of the field in field theory is determined by the scaling of the propagator with distance, because that's what is important when you compute finite diagrams, how everything scale. It would be silly to rescale k and at the same time to rescale h. That's not how you determine the dimension of the field. Omega is 0. Omega is 0. Well, because in the action there is no term phi, but the propagator is the inverse matrix of what you see in the action. Since the matrix is triangular, when you invert it, you get this phi. So yeah, so if you are uncomfortable with this, then you just have to rescale the fields, absorb h in the fields, and then it goes away from the problem. So yeah, so in this language, you can very easily to repeat our calculation that the dimension of O is 2D minus 6. So if we do this, you just take this sum phi I to the fourth operator, you transform it to the Cardy basis, and you find that this becomes 4 omega phi cube plus 6 phi squared sum chi squared. And now if you look at these fields, you see that plus dot dot dot. Plus dot dot dot, and so this dot 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 contains things like phi sum chi cube, phi omega sum chi squared, and phi omega cube. So all these fields have higher scaling dimension, but this field has 2D minus 6 scaling dimension. So we recovered exactly the same result as in this pedestrian method, but with a much computationally much smarter way. Okay, so I'm going extremely pedagogically. I'm basically out of time. Yeah, I can go ahead, but no, I want to go ahead, but it's almost like yeah. So maybe I should.
If you want, you can take a break and continue after lunch.
Well, if people are interested, I could do this. Yeah.
I have to leave.
Yeah.
Doesn't mean I'm not interested.
Yeah. Yeah. Yeah, I think we can view it as sort of as an appetizer to this whole story. Now that we're going to have lunch. So if people, if there are still people who are interested, then I can continue the discussion, let's say at 2 p.m. And I can tell you the rest of the story and probably in another hour. So I'll be moving faster because I already did a lot of elementary introduction. So yeah, let's do it like this. I d omega minus h over 2 omega squared plus d psi bar plus m squared. Here I think I had a mistake. So here's my squared over 2, and here there was 1/2. M squared phi omega plus psi bar plus lambda for omega phi cube plus 12 psi bar. And so what are these psis and psi bars? So psi and psi bar are fields which have fermionic statistics. So they're anti-commuting fields. On the other hand, they don't carry any spinor indices. So these are scalar fields. Thank you. So they don't carry any spinor indices. So these are anti-commuting scalar fields. And of course, in a unitary theory, we are not allowed to have anti-commuting scalar fields. But here, we are not doing particle physics, we are doing statistical mechanics. And so non-unitarity is not really a thing which we should respect or necessarily expect. And so here, yeah, we have an example of a non-unitary theory. And from a realization group point of view, there is nothing wrong with having an anti-commuting scalar field. And so, but otherwise, if you know anything about, if you know or recall anything about supersymmetry, you know how to deal with such Lagrangians which contain both scalars and fermions. You're supposed to form superfields. So here you form a superfield which depends on x, theta, and theta bar, and which is a linear combination of these fields that I introduced. It's phi of x plus theta psi bar plus theta bar psi plus theta bar omega. And in terms of this superfield, you can write the same action. You can reproduce it from the following superspace integral: dx, d theta bar, dx, d theta bar, minus 1/2 phi super Laplacian phi plus v of phi. And this super Laplacian is the normal Laplacian minus d theta bar. Minus h d theta bar. Yeah.
Is some kind of alternative superalgebra with anti-commuting scalar CC generators?
Yeah, so what is the supersymmetry that we are talking about? We have this superspace which has x, theta, and theta bar. And so your superalgebra, it consists of super rotations, so some rotation symmetries of the superspace, which is the supergroup OSP D/2. So it consists of super matrices with D, generalization of orthogonal matrices with D. And on top of super rotations, you also have super translations. So you have a possibility to shift, to move in this theta and x directions by by translation transformations. And so this is the supersymmetry of this theory, and it's called Parisi-Sourlas Supersymmetry.
So this is great. So what you wrote on top is for n equal to 0 limit, right? On top.
Yeah, here it's n equal to 0 limit is already taken.
You were saying that before you start to talk about this representation, that if you are away from n equal to 0, then you have this gap.
Yes.
Can you see it?
You can see it. The way you see it is that you can now perform Cardi transformation. Cardi transformation works for any n, 0 or non-zero. You can perform Cardi transformation at non-zero n, and you can see that at non-zero n in this action there will be new terms, new relevant, extra relevant interactions. For example, you'll get things like n phi squared. So you'll have things like plus n squared phi squared. No, I think without phi, and other things. So there are going to be many other terms which are proportional to n, but they are very relevant, and so they will drive the theory away from the fixed point. So everything is consistent, and so what do we have to conclude? We seem to be reaching this conclusion that there's going to be a fixed point of this Lagrangian which has this supersymmetry. And another important thing that was also observed is that supersymmetry has a consequence called dimensional reduction. So SUSY implies dimensional reduction. So dimensional reduction says the following thing. If you take a supersymmetric theory, which is a theory which is in d dimensions, and now you restrict this theory to a d minus 2 dimensional plane. So in other words, you consider correlation functions where all operators are inserted in a d minus 2 dimensional plane sitting inside d dimensional space. So okay, so in supersymmetry, in the original theory, you had these fields phi, x, theta, and theta bar. So you split x as x parallel, x perpendicular, where x parallel are d minus 2 dimensions, x perpendicular, let me call it x hat. X perpendicular are perpendicular directions, and now you set x perpendicular equal to 0, and also theta and theta bar also equal to 0. And so the dimensional reduction says that if you consider a correlation function in this kinematical configuration, then the correlation function of the supersymmetric field theory has to be equal, is going to be equal to a correlation function of a bosonic theory with the action d phi squared, d phi hat squared, plus v of phi hat, d minus 2 x hat. So, yeah, so in this kinematical configuration, your d-dimensional theory behaves like d minus 2 dimensional theory.
Sorry, how do you see this? You just directly set x perpendicular to 0 in that action?
No, it's more complicated than that. So you can give various arguments for that. I'm not going to review now these arguments. This is a form of supersymmetric localization. So you know, this plane is a fixed point of, so this locus x perpendicular equals 0 and theta equals theta bar equals 0 is in their rotations with respect to the group OSP 2/2. So in this supersymmetric localization, you always restrict your theory to some invariant locus of some superspace transformations. And so here, this locus is this plane. It's not exactly the most standard SUSY localization because we are doing this kind of in space-time. But nevertheless, there are various arguments, either non-perturbative arguments based on SUSY localization, or you can give perturbative arguments based on.
The precise statement is that theory restricted on this kinematics would be corresponding to this.
Yes. And this statement is robust. As far as I know, it's a correct statement. And we were even able to derive this statement from the CFT perspective as a form of some cohomological OPE reduction. So I'm not going to, this is one part of the story that I'm not going to question. I think this part is correct. Why should I pick two orthogonal directions? Well, because the number of orthogonal directions in bosonic and fermionic has to be equal for this construction to work. And so, okay, this is all good and well, but this dimensional reduction property, it leads to this very interesting conclusion. We seem to be leading to this conclusion that the critical exponents of the theory in d dimensions, of the random field Ising model in d dimensions, they have to be equal to the critical exponents of the usual Ising model in d minus 2 dimensions. And this property can be tested by numerical simulations. So one very interesting property of this disordered model, unlike many other disordered models, is that it is very amenable to numerical simulations. So maybe I should say why this is the case. So the point is that if you take Ising model, a ferromagnetic Ising model with arbitrary, even x-dependent magnetic field, it turns out to be, so there was this phase diagram, T and H, and I told you that the interesting point, the fixed point seems to be lying at the 0 temperature. So suppose that you sit at the 0 temperature. Then in order to simulate the model at the 0 temperature, you just have to be able to compute ground states. You pick some random magnetic field, and then for this choice of magnetic field, you have to compute the ground state of your lattice model. Now, it turns out that if all couplings of your model are ferromagnetic, then this procedure of computing the exact ground state of the model is very cheap. There is a polynomial algorithm which allows you to do this computation. And so as a result, people are able to simulate the random field Ising model pretty much in any D. And there are good data about the critical exponents of this random field Ising model. And when these simulations are performed, you find the following thing, that okay, if D is equal to 3, you find some non-trivial critical exponents of the random field Ising model. But we know that if you take D equal 1 Ising model, then the D equal 1 Ising model it only does anything vaguely scale invariant at the 0 temperature, if at all. And so there's no non-trivial CFT in D equal 1. So there's no phase transition, there's no non-trivial CFT. So this theory is completely trivial. The D equal 1 Ising model is completely trivial.
Sorry, why did you say stereo temperature?
I'm sorry?
You said it should be Ising at 2 dimensions lower, but that Ising in 2 dimensions lower should not be a stereo temperature, right? Should be some finite temperature transition. I see the left is stereo temperature.
Yeah.
You said something Ising at stereo temperature. In D equals 1 at stereo temperature.
Well, I'm using the field theory language. The reduction doesn't work at the level of lattice theories. You know, I know that the reduction works at the level of field theories. So I take a certain field theory in 3D, which is scale invariant, and so I should get some theory in 1D, which is also scale invariant. But I know that something is breaking down because in D equal 1 there is no non-trivial scale invariant theory. So I'm reaching a contradiction basically.
Maybe I misheard, but it sounded like you're saying this D equals 1 theory must be at zero temperature.
I know at zero temperature, what I only said is that that the only scale invariant behavior of the D equal 1 Ising model is at zero temperature, and it's completely trivial. Yeah. So if you now look at the D equal 4 case, then again you have some non-trivial critical exponents here, and in D equal 1 you also, I mean, in D equal 1 we have Ising, so we know exact critical exponents, but the problem is that the D equal 4 critical exponents do not agree with D equal 1 critical exponents. So the whole thing doesn't work again. And so, well, at that point, people gave up on this idea, and they said that perhaps it only works in perturbation theory around 6 dimensions, but it doesn't work in any other dimension. But then the simulations in D equal 5 were performed, and again they found some critical exponents, and now, lo and behold, they found critical exponents which agree within error bars with the D equal 3 critical exponents of the Ising model. And moreover, by even some a little bit more subtle numerical simulations, they even found evidence for supersymmetry in 5 dimensions. So now, you know, and it's, you know, I'll write some names, but if you're not in the field, you probably first time you heard them. So there is Fitas, there is Martin Meyer, Pico, and other people. And so, okay, when you see something like that, what is your guess? What's going on? Like as a field theorist, if you are facing this puzzle, you know, I gave you a certain derivation, and here's the experimental results. So what would be the best guess for what is going on? I'm sorry? There's not a unique fixed point. Yeah, that's I agree. But why is there not? So what's wrong with the supersymmetric fixed point? It's unstable. Yeah. So the most like I think for someone who's been around, the most natural interpretation of this phenomenology is that, you know, there is some instability in of the supersymmetric fixed point. And if there is this instability, note that the Cardy argument even kind of allows for chasing out this instability, because recall, okay, I erased now the thing, but there were some dot, dot, dot terms which we erased when we passed to the Cardi-Lagrangian. And we said, okay, well, those terms it looks like they're irrelevant. And in d equals 6 minus epsilon, they're definitely irrelevant. But who knows what's going to happen about those terms when we lower the dimension? So, one scenario that we set out to explore with Apratim and Emilio is that perhaps something like that is happening, that you have a family. Let me draw a picture in the theory space. So this is a theory space. And this is D. And so for any D, there is a theory, there is a Gaussian theory. So Gaussian theory exists for any D. Then we said that at D smaller than 6, there exists this new theory, there's this new line of theories, which is a line of SUSY fixed points. It splits off of the line of Gaussian theories in D equals 6. And then, based on this phenomenology, we are led to believe that there is a certain critical value of D critical, such that there is a new line of fixed points which splits off. So these are the line of non-SUSY fixed points. And for D below D critical, the SUSY fixed point is unstable with respect to some SUSY breaking perturbation. And so, in fact, the true fixed point which describes the critical behavior is the non-SUSY one. So, is this a reasonable conjecture?
Why would the new non-SUSY fixed point have to appear there? Couldn't it exist in 6 minus epsilon and simply become stable at DC?
A good question. Indeed, we don't know if this SUSY fixed, perhaps, we don't know if this fixed point existed also below, above D critical.
Because this happened with the line and Q, because you just exchanged stability some place before. Indeed. The important thing here, a very important thing here, is that this SUSY fixed point and the non-SUSY fixed point, they have different symmetry. So, of course, because SUSY is supersymmetric, non-SUSY has smaller symmetry. So if they had the same symmetry, then such a thing could not happen, because the theories which have the same symmetry, they can only appear in pairs or annihilate in pairs, but they cannot split off one from each other. Since this theory has a different symmetry, it can get split off. Now, whether it exists on another side or not, it's there's no general argument. So in some situations it may exist on both sides, like in the cubic case that you're mentioning. In other examples, it can exist just on one side, because it could be that the theory on the other side has a wrong sign of coupling, and maybe it's not a well-defined theory. And when you say different symmetries, you mean local or global?
I'm sorry?
Okay, it's non-SUSY, but do you also mean it has a different global symmetry?
Global symmetry here is always going to be SN in some sense. No, it's the space-time symmetry is different. And okay, so basically, to make a long story short, in our work we found support for this scenario. So we found some operators which are dangerously irrelevant operators. So what does it mean? It means that if we are close to 6 dimensions, these operators are irrelevant, And so their presence does not modify, does not destabilize the SUSY fixed point. But as you move lower and lower in dimension, then these operators, they get negative anomalous dimensions. And beyond certain d-critical, these operators become relevant. And since these operators break supersymmetry, there is a potential for them to, to realize this scenario. So now what I could tell you is how exactly we classify these operators and how exactly we do the calculations and what are exactly the epsilon expansion results for these operators. But given that I'm already half an hour over time, I'm not sure if I want to go in this direction. But there's one more thing I wanted to tell you, which is related to branched polymers. But first there's a question.
So, when you say that the exponents are related to those in Ising, you essentially say that there's a subset of operators in this theory whose dimensions are like in one-to-one corresponding to the operators in Ising, right?
Yeah.
Then there should be more operators in this theory, and some of these additional operators are the ones that become dangerously irrelevant.
So there are two questions here. The first question is about supersymmetric theory. So as I said, that the supersymmetric theory, it projects down to this non-supersymmetric theory upon reduction. Now, even supersymmetric theory contains some operators which under reduction project to zero. Because the primaries or the superprimaries of the supersymmetric theory, they are classified by Young tableau of the Parisi-Sourlas superrotation of this OSP d/2, and the primaries of the d-2 dimensional theory, they are classified by the Young tableau of the d-2 dimensional rotation group. And so it turns out that there are more Young tableau for this OSP d/2. And so some operators project down to zero. So the d-2 dimensional theory, it tells you scaling dimensions of many, many operators of the d-dimensional theory, including the dimensions of the most interesting ones, like phi, phi squared, and so on. But it doesn't tell you everything about the d-dimensional theory. So now the second part of the question is, what are these interactions which destabilize the SUSY fixed point? So here there are three types of operators which can destabilize the SUSY fixed point. You are driving me to the point which I wanted to skip actually. So, but this is kind of a juicy part, so I might sell this anyway. So the first part of operators is what we call SUSY writable operators, the first class. So these are some operators which exist. So these are operators which exist in the SUSY theory. But an operator which exists in the SUSY theory, it doesn't have to be a singlet. It doesn't have to be a supersymmetry singlet. There's some SUSY multiplet. The multiplet contains some components, many components. Some of these components preserve SUSY, other components break SUSY. So if you take a SUSY breaking component added to the action, then it's going to break SUSY. So these are the SUSY writable interactions that we consider. And then there were two other types of operators. There were operators which are called SUSY null, and there are operators which are called non-SUSY writable. So non-SUSY writable operators, let me explain those. These are operators which cannot even be written in the SUSY variables. So imagine an operator which is something like, omega chi I cube or something like that. We don't know how to transform these operators to SUSY variables. We know only how to transform to SUSY variables operators built out of an even number of chi's, only things like chi squared. But yet these operators, they existed in the original theory before we passed, so after we did the Cardi transform and we replaced phi i's by phi omega and chi I, these operators, they exist in the theory. And when you go to the SUSY variables, when you replace chi I by psi bar, these operators are completely erased from your theory. Which means that, I mean, they are not visible, but they're still there. So you can still analyze these operators if you work in this original chi I, phi omega chi I basis, and that's what we had to do. So there are these sort of operators that you have to analyze. And finally, the SUSY null operators, these are weird operators. For example, the simplest class is chi I squared. So this operator, if you go to the SUSY variables, it becomes psi bar squared, and it vanishes because psi's are anti-commuting scalars. And so you could say, oh, but these operators don't really matter. I mean, they're not important. But in fact, you can. Indeed, they are less important than these non-SUSY writable operators. But you can imagine situations where the SUSY null operators are also dangerous. And so, in fact, in our work, we found one of these guys which was becoming relevant, and one of these guys which was becoming relevant. But these SUSY writable guys, all of them were irrelevant.
Is this writable operators a sign that some operators in the original theory become non-local?
No, it's not a sign of that. It's just a sign that the SUSY theory, it doesn't really capture, even if the SUSY fixed point is realized, it doesn't capture, the SUSY theory doesn't capture the full dynamics of the Parisi-Sourlas.
So maybe the SUSY theory is a subset of larger form.
My view is that, okay, there is this fixed point theory, which is huge, and the SUSY theory describes a big sector of it, which contains many interesting operators, but not all operators. For example, these non-SUSY writable operators, it doesn't even capture them. So if suppose that you are sitting suppose you are in 5 dimensions, and in 5 dimensions, suppose that it is indeed true that the SUSY fixed point is reached. Then, and for some reason, you still want to know the dimension of this non-SUSY writable operator. Well, it's some scaling operator of your theory. You cannot extract it from the SUSY theory. You have to do an independent computation. It's like a new sector of the theory which doesn't speak to the SUSY theory. Can I write them down in terms of microscopic fields? Yeah. Well, the ones which are the ones that we were found particularly interesting. I mean, the one which we found particularly interesting is the so-called Feldman-6 operator, and in terms of microscopic variables, it looks like sum phi I minus phi j 6. You see, it's an ascending operator, and if you transform it to the Cardi basis, then it becomes sum chi I cube squared minus 3/2 sum chi I to the 4th sum chi I squared. So since it has chi I cube and chi I to the 4th,
I cannot transform it to the SUSY variables.
The quartic one is not appearing? Like before?
I'm sorry?
The quartic one is not appearing?
The quartic one is a SUSY null. The F4, you can also consider F4, which is the same thing with 4 instead of 6, and that operator is precisely chi squared squared, it's SUSY null.
But it also becomes dangerous?
It also becomes dangerous, yes.
That would be my favorite.
Yeah, chi squared squared, it's one of our potential candidates. So, okay, what else can I say here just to spice this up the discussion is that this whole story, if we are right, there is a smoking gun to our scenario, which is that if you sit in 4D, suppose we are in 4D, if we are right, then the supersymmetric fixed point exists even in 4D, it's just unstable. So there is a non-supersymmetric fixed point which is stable and supersymmetric one which is unstable. But, you know, if it's an unstable fixed point, it's something like a tricritical point. So we know that the tricritical points, they can also be realized in the Monte Carlo simulations at the expense of extra tuning. So we are making a prediction then that even in 4D, so in 4D people can do Monte Carlo simulations of these models, that they should be able to find this supersymmetric values of critical exponents by performing some extra tuning.
But then you are not sure whether it's tricritical or quadricritical. Yeah.
We are not sure if it's tricritical or high critical. We are not sure. We are not sure about that. But okay, let's suppose that it's tricritical. And so we made this prediction. And actually, when we made this prediction, I was not very hopeful that this prediction is going to be realized anytime soon, because I know that these people who do these simulations, they work very hard, and it's really hard job to do these things. And if you have to tune something, it becomes even harder. But as a matter of fact, I was told by Marco Pico that they will actually be able to see it. And so they are still checking the results, but it turned out that there was a so what they tune is the shape of the distribution of the magnetic field. So when you do this Monte Carlo simulations, you have to pick some distribution for the magnetic field P of H. So you can pick it. You can choose it to be Gaussian. Or maybe you can choose it like a double peak distribution or something like that. And there has to be some universality that whatever distribution you pick, the fixed point should be the same. Except that if there are three critical points, then you may be able to find one by tuning this distribution. And it looks like by tuning this distribution to be double peak Gaussian, they are able to see that at least there is a new fixed point in this regime. They are not yet able to see if it's supersymmetric or not, but they tell me that the values of the Binder cumulant and other things which they observe in this regime are different from the values of the Binder cumulant that they observe in that regime. So it looks like a new fixed point. So maybe
Do you know which 2D series it is? If this SUSY one continues,
they should see 2D Ising critical exponents.
we should see 2D tricritical.
No. 2D normal 2D Ising.
Okay, because it's for
Because it's yeah.
Plus maybe something else that is relevant information.
Well, they're tuning this away. They're tuning it away. But
In the tuning, the Gaussian correction is
They could see many things, but for the moment, they can only tell me that they see that there is a new fixed point, but the properties of this fixed point they are still investigating. So it's pretty exciting. Well, I could say something about branched polymers, but I don't know. Like, who wants to hear about branched polymers? Few people. Anyway, then let me skip branched polymers. If you're interested, I can tell you during coffee break. So I'll stop here. Since I'm being my own chairman, are there any questions? Yeah.
Why not measure the non-SUSY one first and one Pablo?
They measured it already. They measured, yeah, and they found that it has critical exponents which are not in agreement with 2D Ising, and it's not in agreement with SUSY.
I think in the simulation it will be very difficult to completely tune it away. I think what will happen that you still have instabilities, but they will just come later, probably at a scale which is bigger than your system size. So you might be able to see some physics behavior, but will not be the asymptotic behavior.
But if what you were saying were true, then one could not, say, measure critical exponents of the three critical Ising model in a numerical simulation, but we know that it's not true. One can measure critical exponents of three critical field theories in numerical simulation.
Yeah, but here the mechanism, I mean, I tried to do this in the free theory.
Yeah.
Simpler, and then, so if the microscopic disorder is a Gaussian,
Yeah.
so then there is an RG equation which will reduce the cusp.
Okay.
You can delay this cusp if you take it to the minus x, 5 to the 4, the quartic correlation function. Then the standard cusp mechanism, the thing which breaks supersymmetry, does no longer hold, but somehow the disorder still knows, and then comes some later scale, much later scale, but it still comes.
Just to make sure, what you are saying is based on your experience with another model, with a model which doesn't have 5 to the 4th interactions.
Yeah, but I don't think there's any fundamental difference.
Well, there is, because this whole Cardiff story only works because there is 5 to the 4th interactions. So in the model that you are familiar with has a shift symmetry, it doesn't have 5 to the 4th interaction, so physics is pretty different. I think I reserve my judgment. Let this numerical simulation people do it. If they find SUSY, if they find a SUSY fixed point, the fact that they're tuning the disorder distribution, you are saying that it looks very different, but from the point of view of RG, tuning the disorder distribution after you integrated out the disorder translates into tuning coefficients of operators in the effective Lagrangian. So from that point of view, there doesn't seem to be any fundamental difference. Yeah.
From field theory, can there be some information about which parameter you are tuning? You should be tuning.
Yeah. You can.
That's why we are doing this double tuning.
Yeah. That's what we wrote in our paper. So what you can do is that you can perform a Hubbard-Stratonowitz transformation on the lattice in a theory which has a general disorder distribution. And you can see that when you do this, this amounts to adding some extra phi to the whatever terms to your effective action. So you know that by tuning disorder is the same thing as tuning in some direction operators in the action. Of course, you have to be a little bit lucky, because tuning disorder, you just have a one parameter space of theories. You have to be a little bit lucky that that one parameter space is precisely what you need to to reach this critical point. That's why we were not very hopeful that we will be able to do it so easily.
You are following the second order line, so it needs any sum.
Yeah, but what could have happened is that somehow you run out of parameter space, but that's apparently this is not what is happening. Okay, so if somebody has any more questions, I'm happy to answer them in private.